Hey guys, today we're going to learn about trigonometric functions on the unit circle. So we've already learned how to find trigonometric values from a point that is on a circle on the coordinate plane. Now the unit circle just indicates that the length of radius r, right, the radius, is going to equal to 1. That's why it's called the unit circle, 1 unit. So like I said, the radius is equal to 1. Now previously we learned that the sine of theta is equal to y over r. Now on the unit circle, if the radius is 1, that means that the sine of theta will just equal to y, since it would be y over 1. Cosine of theta we learned is x over r. Same concept. Since r is equal to 1, then x over 1 is just going to equal to x. Tangent remains as y over x, but now cosecant is going to equal to r over y, and r is 1, so cosecant would be 1 over y. Secant is r over x, so secant on the unit circle will be 1 over x. And cotangent would remain the same, the reciprocal of tangent, so x over y. Now let's look at the full unit circle, because here all we see are just a few coordinates. And just to illustrate again that the radius is 1, look at these coordinates. Here, on the positive x-axis, the x would equal to 1 because the radius is 1, etc. So let's look at the unit circle. Now this can be very overwhelming, but we're going to break down the unit circle. You are going to be, in the future, if you have me next year for calculus, you will need to know the unit circle very well. But really, all you really need to know is the first quadrant, because we're going to develop patterns on how to figure out all of the other values of the unit circle without needing to look at it and just knowing quadrant 1. Now you'll see that the unit circle has the degree measures and then its corresponding radian measures. These are the angles. So 30 degrees is the same as pi over 6 in radians. So here we already have their conversions. So we have the 30, the 45, and 60, which corresponds to pi over 6, pi over 4, and pi over 3. Now remember that a full revolution is 360 degrees. So this is, although it says 0 degrees, it is also 360 degrees. And although this is 0, if I were to write down a full revolution in radians, we learned that a full revolution would be 2 pi. So that's why you'll see here at the axis, it goes by pi over 2, since 2 pi divided by 4 equal parts is pi over 2. So here we have pi over 2, which is equivalent to 90 degrees. Here we have pi, because pi over 2 plus pi over 2 is 2 pi over 2, which is pi, which corresponds to the 180 degrees. And then 2 pi over 2 plus another pi over 2 is the 3 pi over 2, which corresponds to 270 degrees. Then 3 pi over 2 plus another pi over 2 would give me that 4 pi over 2, which is 2 pi. Now, we're going to need to develop patterns in terms of the radians, because with the degrees, it's very easy to figure out what quadrant we're in just based on the numbers. If we know that this is 90, 180, and 270. If I tell you what quadrant is 135 located, we know that it's more than 90, less than 180, so quadrant 2. So we're going to develop patterns for the radian measures. Now, if you'll notice first, there is a denominator pattern. If you look at each quadrant, the denominators go 6, 4, 3, and then 3, 4, 6. 6, 4, 3, 3, 4, 6. So that's the pattern with the denominators. 6, 4, 3, 3, 4, 6, and etc. because it just continues in that pattern. Now we're going to look at the numerator pattern for these radian measures. In quadrant 1, the numerator is just pi. So if I ask you, where is pi over 4, you would know that it's in quadrant 1 because the numerator is just pi. In quadrant 2, if you look at the numerator is 1 less than the denominator. So 2 is 1 less than 3, so 2 pi over 3. 3 pi over 4 5 pi over 6. So the numerator pattern for quadrant 2 is that the numerator is 1 less than the denominator. Now in quadrant 3, it's the other way around. Now the numerator is 1 more than the denominator. See, 7 pi over 6, 5 pi over 4, 4 pi over 3. That numerator is 1 more. So that's the pattern for quadrant 3. Numerator is 1 more than the denominator. Quadrant 4, the pattern may not be as evident, but here's the trick. If you look at the denominator and you multiply it by 2, you get 6. And then subtract 1, 5. Over here, 4 times 2 is 8, minus 1, 7. 6 times 2 is 12, minus 1, 11. So this means that the numerator is 1 less than double the denominator. So that's going to be your pattern, and we're going to be using these patterns later on in the lesson. Now, how do we use the unit circle? If you notice here that I put in the right-hand corner, we haven't even discussed these coordinates. The coordinates represent the cosine and the sine value. Remember that here we established that on the unit circle, sine is equal to y and cosine is equal to x. So that means that when we look at these coordinates, the x value is the cosine value at that angle, and the y value is the sine value at that angle. So if I ask you what is the cosine of pi over 4, you would look at the x and it would be the square root of 2 over 2. If I asked you what is the sine value of 210 degrees, we would look over here and the sine value would be negative 1/2 because that is the y. So let's practice that. So right now we're just going to read the unit circle. First, we have the sine of pi over 3. If I want to find the sine of pi over 3, that means I'm going to look here at my unit circle. Here's pi over 3, and I get square root of 3 over 2. So this sine value will be the square root of 3 over 2. If I ask you for the cosine value of 135 degrees, again, we look at the unit circle, we look for 135, and I'm looking for cosine, so that will be the x value, which is, oops, I'm at the wrong angle, over here, negative square root of 2 over 2. Now the unit circle only has the values for cosine and sine. But if you have cosine and sine, you can figure out all the other trig functions. So like here for C, we're trying to find the tangent of 270. Tangent is equal to y over x. Or remember our quotient identities, it's the same as sine of theta over cosine of theta. Which remember on the unit circle, sine is y, cosine is x, so all of this makes sense. So if I want to find the tangent of 270, we're going to go to the 270 degrees, which is here, and these are my coordinates, 0 and negative 1. So the cosine of 270 is 0, and the sine is negative 1. So if I'm going to plug this in, the y is negative 1, the cosine is 0. But here we have 0 in the denominator, so that means that this value would be undefined. So there is no tangent of 270. Now for the secant of 7 pi over 4. Secant, remember, is the reciprocal of cosine. So it would be 1 over x, or 1 over cosine. These are the same. So I'm going to go to 7 pi over 4, which I know this is going to be in quadrant 4 because the numerator is 1 less than double the denominator. And then I'm going to note what the cosine is. So here's 7 pi over 4, and the cosine is the square root of 2 over 2. So the secant of 7 pi over 4, I don't know why I'm rewriting this, is the reciprocal of square root of 2 over 2. So that would mean 2 over the square root of 2. But remember, we can't have a square root in the denominator, so we would rationalize this. And I would get 2 square root of 2 over 2, which the 2's would cancel, and that would give me a final answer of square root of 2. Now, another thing to take note on the unit circle. So let's go back here a second. If you look at your cosine and sine values, the numbers never change as long as the denominators are the same. So look at in quadrant 1 for pi over 6. The cosine is the square root of 3 over 2, and the sine is 1/2. If I go to quadrant 2 to 5 pi over 6, right, same denominator, you see that the actual values are the same. The only thing that changed is the sign. Same thing here in quadrant 3 at 7 pi over 6. Same values. It's just the signs may change. And 11 pi over 6, again, same concept. Now, how do I know what signs things are going to be is remember that ASTC, all students take calculus. So you'll notice that all of our values in quadrant 1 are positive, and that's because we're on the positive x-axis and the positive y-axis. In quadrant 2, only sine is positive. So you'll notice only the y values are positive, which correspond to sine. And that's because here in quadrant 2, we have the positive y-axis, the negative x-axis, and that's why the cosine values are all negative. In quadrant 3, you'll notice that only tangent is positive, and that's because we have negative x's and negative y's. And tangent is when you divide y over x, so a negative divided by a negative would give you a positive number. In quadrant 4, only cosine is positive. So you see here that all of the x values are positive, which correspond to cosine, and all of the y values are negative. And again, all of this makes sense because of where it's located on your grid here. Because quadrant 4 is on the positive x-axis and the negative y-axis, that's why all of those x's are positive. So now let's see how we're going to find these trigonometric values of any angle. And before we do that, we would need to figure out what is a reference angle. Now, most of the time we evaluate trigonometric functions for angles that are greater than 90 or pi over 2, and all negative angles. So we can do, like, a little shortcut would be to figure out what is a reference angle, because it's going to help us calculate for any trigonometric function on the unit circle without having to memorize the whole thing, because that can be kind of annoying, having to memorize the entire unit circle. So a reference angle is basically a positive acute angle that is closest to the x-axis. So you'll see here that we have various examples. If your angle, I just noticed that these are switched. But if your angle is in the first quadrant, which is actually this graph here, the reference angle is the same as the angle given in the first quadrant. If your angle is in the second quadrant, which is over here, right, then the reference angle would be the acute angle that goes to the x-axis. If your angle is in the third quadrant, then same thing is that red part here. And then in the fourth quadrant, it's always the angle that is closest to the x-axis. So for example, here I gave this diagram. If your angle is 150 degrees, the reference angle would be the 30. It is the acute angle closest to the x-axis. And 30 degrees is in quadrant 1 of our unit circle. And I'll explain what to do with the reference angles after we figure out what the reference angles are. So let's determine how to find a reference angle. So in quadrant 1, if your angle is in quadrant 1, then that is its own reference angle and you don't have to worry about it. So we're only going to look at quadrant 2, 3, and 4. So if this is my angle here, this will be theta. My reference angle would be this one here, which is marked by theta and then a tick mark which is called prime. So that would be your reference angle. So think about how we find that angle. Let's say if this angle is 120 degrees. In order to find this acute angle, it's closest to the 180. So we would do 180 minus the 120 and we would get 60 degrees. And that would be our reference angle. Now over here, let's say I have this angle. Let's say that this angle is, I don't know, 210. Now 210 is closest to, again, this 180. Our reference angle would be this angle here. So to figure out what that angle is, we would do 210 minus the 180 to get 30 degrees. So that would be my reference angle here. And notice that all of these reference angles that I'm finding, these are all located in the first quadrant of the unit circle. And that's why I was telling you at the beginning that as long as you know your first quadrant, you can figure out the trigonometric values of any angle. Okay, so this last one here, let's say that this angle is, I don't know, let's say 300. This one is closest to this axis here, which is 360, because you would complete a full revolution. So if this is my angle, my reference angle, theta prime, would then be 60 degrees, because we would do 360 minus the angle. And exactly what I was showing you here is what I have outlined here for you. Now, if we were doing radians, instead of doing 180 minus pi, 180 corresponds with pi, so pi minus theta, and so on and so forth for replacing your 180 with pi and 360 with 2 pi. However, I'll show you a shortcut with finding a reference angle for the radian measures. So let's just do that. Let's figure out the reference angle. And then we're going to figure out what quadrant does the original angle lie in. So the first thing that we would need to do is to find a positive angle that is less than 360 or 2 pi that is coterminal with the given angle. That's always going to be your first step. Then you're going to draw the angle in standard position and note the quadrant where it lies. Now, when I say draw the angle in standard position, this does not necessarily mean you have to go through all of those steps that we did in a previous lesson. We can just estimate where the angle will lie. We just want to know what quadrant it's in, so it does not have to be perfect. Then we're going to use the drawing to find the reference angle for that particular given angle. So let's start with 345. 345 is already less than 360, so I don't need to find a coterminal angle. Now, if I think about where it's located on my axis here, 345 is less than 360, but more than 270, which is down here. So 345 is somewhere over here. This is in quadrant 4. So to figure out the reference angle, which is this one, we would have to do 360 minus 345, which would give us 15 degrees. And this would be the reference angle. Now, for theta is equal to 5 pi over 6. 5 pi over 6 is in quadrant 2. And I know that it's in quadrant 2, again, because the numerator is 1 less than the denominator. So this is my angle. So the reference angle is this one here, the one closest to the x-axis. This is pi. So to figure out that angle, we have to take pi and subtract the 5 pi over 6. So theta prime is going to equal to pi minus 5 pi over 6. In order to be able to subtract, we need to rewrite this so it has a denominator of 6. So I'm going to put this over 6 and multiply this by 6, and I get 6 pi over 6 minus 5 pi over 6, which will give me pi over 6. And that would be my reference angle. So a little shortcut for radians. If you're trying to figure out the reference angle, it's just going to be pi over whatever the denominator is. See here, the denominator was 6. So if I do pi over 6, that would be my reference angle. Now for C, I have a negative angle. So what I first need to do is find a coterminal angle that is positive but less than 360. So first, I'm going to figure out that coterminal angle. So I have that negative 135 degrees, and I'm going to add 360. Since remember, that's how you find your coterminal angles. You either add or subtract 360 degrees. When I add, I get 225 degrees. So this is my positive coterminal angle. Now, if I think about where that lies, this is 180, this is 270, so 225 is in quadrant 3. That means to find the reference angle, it is this angle down here. So to figure out that angle, that's the one that's closest to the 180, but 225 is more. So I would need to subtract 225 minus 180, which would give me 45 degrees. And this would be my reference angle. Now over here we have 580 degrees, which again is more than 360, so I need to find that positive coterminal angle less than 360. So I'm going to first subtract 360 to get that coterminal angle. 580 minus 360 is 220. Now we're going to think about where does this angle lie. So I'm going to draw here my little coordinate grid. 220 is more than 180, so it'll be around here somewhere. That means that my reference angle is this part there. So that would be theta prime. In order to find that angle, same as we did over here for C, I would have to take 220 and subtract 180 to get that little part there. And 220 minus 180 is 40 degrees. So this would be my reference angle. For 8 pi over 3, we don't necessarily need to do much work. My reference angle is going to be pi over 3. However, you will in the future need to know at least what quadrant this lies in. Now, this quadrant, 8 pi over 3, is more than 2 pi. And I know this because, first of all, it doesn't follow any of the patterns of my denominators. See, this is 8 over 3. And if I double the 3, I get 6 minus 1 is 5. So it's more than quadrant 4, meaning that it's going to be more than 2 pi. So I would have to subtract 2 pi to figure out what quadrant it's in. So I'm going to put this over 3, meaning multiply the numerator by 3, and I get 8 pi over 3 minus 6 pi over 3. Which is equal to 2 pi over 3. So that is my coterminal angle, and 2 pi over 3 would be in quadrant 2. Last one here, we have theta is equal to negative 13 pi over 6. Now again, I don't really need to do much work to figure out my reference angle. That's going to be pi, and then over whatever the denominator is, which is 6. But I will need to know what quadrant this is located. Since this is a negative angle, I'm going to want to add 2 pi. I'll need to put this over 6, so multiply this by 6. Oops. And I would get negative 13 pi over 6 plus 12 over 6, which would give me negative pi over 6, which is still a negative angle, so I'm going to add another revolution. So I'm going to add 12 pi over 6, and I get 11 pi over 6. Now 11 pi over 6 follows that denominator pattern. The numerator is, the numerator is 1 less than double the denominator, so this angle is located in quadrant 4. So now that we know how to find reference angles, let's see how we use them. So like I said, we don't necessarily need to have the entire unit circle memorized. We just need to know quadrant 1. So, and the reason for that is the reference angles. If I go back to my unit circle a second, as long as I know what my reference angle is, since it's always in quadrant 1, remember I said that these values for cosine and sine never really change. The only thing that changes is the signs. So if I know what quadrant my angle lies in, I know what the sign of the trigonometric function will be because of ASTC. But I can use my reference angle to figure out what the value actually is, like the numeric value. So let's say, for example, we know that the angle we have, or we're trying to evaluate, is 135. Let's say for the cosine of 135. The cosine of 135, we can see here, is negative square root of 2 over 2. But let's say I didn't know that, right? The reference angle to 135 would be 45 degrees. So 45 degrees corresponds with the 135 degrees, because this would be the reference angle. In quadrant 2, cosine is negative. So if I know that the cosine of 45 degrees is square root of 2 over 2, then I would just put the sign in front. Negative square root of 2 over 2 would be the cosine of 135. So that's how that kind of works. And I kind of went over that really quickly, but let's go over this now a little bit slower. Okay, so let's work with this first one here. Find the value of tangent of 120 degrees. So first, we're going to note the quadrant and sign of the trigonometric function you are evaluating for. So this is my angle. 120 degrees is more than 90, but less than 180. So it's going to be here somewhere in quadrant 2. And in quadrant 2, tangent is negative, since in quadrant 2, only sine is positive. Now we need to find the reference angle. Here, in order to find the reference angle, it's this one here. That means I would have to take 180 and subtract the 120. And I get 60 degrees. So what I do now is that I find the function value for the reference angle. So I'm going to figure out what is the tangent of 60 degrees. Now the tangent of 60 degrees, that is the sine of 60 divided by the cosine of 60. If you have your first quadrant of the unit circle memorized, you know that the sine of 60 degrees is the square root of 3 over 2. And the cosine of 60 degrees is 1/2. So now we have to divide these fractions. And remember, when we divide fractions, it's the square root of 3 over 2. We copy, right? Then we change to multiplication, and then we flip 2 over 1. The 2's here will cancel, and I'm left with the square root of 3 over 1, which can just be written as the square root of 3. So what this means is that the tangent of 120 degrees is going to equal to, it's negative because it's in quadrant 2, but the actual value is the same as the reference angle, so square root of 3. And that's how we use reference angles. Again, just to kind of reiterate, right? Your reference angles will give you the trigonometric function value of any angle on the unit circle. So as long as you can figure out what the reference angle is, you don't need to memorize the entire unit circle. You just need to know that first quadrant. And another thing to note about the unit circle in the first quadrant is that these values, even though it looks a little bit overwhelming, they're very repetitive. If you look at pi over 3, it's 1/2 square root of 3 over 2. And then at pi over 6, it's the exact same numbers, but just switched. So instead of 1/2 being the x, it is the y. Instead of square root of 3 over 2 being the y, it's the x. And then for pi over 4, 45 degrees, it's the exact same value. Square root of 2 over 2, comma, square root of 2 over 2. So there's not really a lot to memorize, you just have to know the order. Okay, so now let's put this all together. Let's start off here with the sine of 300 degrees. So first we need to figure out what quadrant this is in. 300 degrees is somewhere over here in quadrant 4, since it's more than 270 but less than 360. And we know that in quadrant 4, only cosine and secant are positive. That means that sine is negative. So we already know that our final answer here will be a negative value. Now we need to find that reference angle. Since this is the 300 degrees, my reference angle would be this piece here. So in order to find that leftover piece, it would be the full revolution, right? Because this would make a full revolution, minus the 300. So that gives me 60 degrees. Now we're going to find the sine of 60 degrees, which again, you need to start practicing remembering that first quadrant. The sine of 60 is the square root of 3 over 2. So that means that the sine of 300 degrees is going to equal to negative square root of 3 over 2. And this would be my final answer. Now you can look at the unit circle to confirm this answer. So we just did the sine of 300. Here's 300, negative square root of 3 over 2. Let's go over the tangent of 14 pi over 3. First of all, I notice that this is more than a full revolution, so I'll need a coterminal angle. So theta is going to equal to, now I'm going to do 14 pi over 3 minus 2 pi, which I'll need to put it over 3, so I'm going to multiply this by 3, and I get 14 pi over 3 minus 6 pi over 3, which would give me 8 pi over 3. 8 pi over 3 is still more than 2 pi, so I'm going to subtract again. 8 pi over 3 minus 6 pi over 3 gives me 2 pi over 3. So this is my coterminal angle. And I did this just to be able to figure out what quadrant we're in. 2 pi over 3 is in quadrant 2. And in quadrant 2, only sine is positive. That means that tangent is going to be negative. So that's what we're going to keep in mind. Our final answer here will be a negative number. Now we need to find the tangent. Well, sorry, I need my reference angle. Remember the shortcut here? Our reference angle is just going to be pi over whatever the denominator was, which is 3. So now I need the tangent of pi over 3. In quadrant 1, remember that tangent is y over x. And if you look at pi over 3, the y value is the square root of 3 over 2, and the x value is 1/2. So we copy, change, flip here. We get the square root of 3 over 2 times 2 over 1, which will cancel, and that will give me the square root of 3 over 1, or just the square root of 3. So this is the actual numeric value. So that means that the tangent of 14 pi over 3 is going to equal to negative, because that's the quadrant, that's the sine of tangent in quadrant 2, negative square root of 3. And that would be our answer. Now let's look at this last example. We want to evaluate for the secant of negative 17 pi over 4. So first we need to find a positive coterminal angle so we can determine what quadrant we're in. So these are always the steps that you follow. If you need to, you find the coterminal angle, identify the quadrant so you can identify the sign of the value, and then evaluate for the reference angle, and then evaluate the secant of the reference angle, and then apply the appropriate sign. So first we're going to get that coterminal angle. So we have negative 17 pi over 4. So I need to add 2 pi, which I need to put over 4. So I'm going to multiply 4 to the numerator as well. So this is going to be negative 17 pi over 4 plus 8 pi over 4, which will give me negative 9 pi over 4. Still negative, so we have to add another 2 pi, which is the 8 pi over 4, which gives me negative pi over 4. But it's still negative, so I'm going to add one more time, and I get 7 pi over 4. So this is the positive coterminal angle. Now, this is in quadrant 4, and I know it's in quadrant 4 again because of the pattern of the numerator. The numerator is double the denominator minus 1. And in quadrant 4, secant, if you think of all students take calculus, right? Quadrant 4, cosine is positive. That means its reciprocal secant is also positive. So my answer will end up being a positive number. So now we need our reference angle. Remember that the shortcut is that it's always pi over whatever the denominator is, which is 4. So now I need to evaluate for the secant of pi over 4. Secant is the reciprocal of cosine. So again, if I look back at my unit circle, which you can, or you should know the first quadrant, but if I look here at the first quadrant to get the secant of pi over 4, the cosine is square root of 2 over 2, so the reciprocal would be 2 over the square root of 2. So that would be the secant. But again, we would have to rationalize this. So I'm going to multiply by the square root of 2 over the square root of 2, which gives me 2 square root of 2 over 2. Those 2's would cancel. So the secant of pi over 4 is the square root of 2. Now we write down our final answer. The secant of negative 17 pi over 4 is going to equal to, and it's positive, so positive square root of 2. And this would be my final answer. And that's evaluating trigonometric functions on the unit circle.